Good evening, class. We are looking at the chain rule. So we've looked at a lot of rules and we are adding the chain rule. The chain rule pertains to composite functions when we have a function of f of g, which is f of g of x. The derivative is f prime of g of x times g prime of x. And in Leibniz notation, dy dx is dy du dx. What do we mean by that? Let's discuss that. Okay, first and foremost, the idea of a composite function. I hope everybody remembers that. That's a basic algebra. If f of x is x cubed and g of x is 1 plus x squared, let's find f of g as well as g of f. Let's quickly refresh everyone's memory. So f of g or f of g of x, you replace the x in x cubed with 1 plus x squared, and that's what you have. In the case of a g of f, the answer is g of f of x. And that means you replace the x in g with x cubed. And since this is doable in one shot, we can write it as 1 plus x to the power of 6. And as you can see, they are not equal. By the way, in general, f of g is not equal to g of f. They only become equal when the two are inverse functions. All right. Why do we learn the chain rule? If you are interested in differentiating expressions such as y equals square root of 10x plus 5, or f of x equals 10x squared minus 1 to the power of 50, we need that. So the chain rule basically says the following. So if you want to take the derivative of that, f is the shell function. So you differentiate the shell function over g of x. And by the chain rule times the derivative of the inside makes it g prime of x. If we go with the Leibniz notation, y is a function of u is a function of x, and then dy dx becomes dy du dx. What do we mean by that? We'll make it clear with a couple of simple examples. So that's another way of writing it. Okay, that's the same thing that we have over there. And here's the general power rule. That may be interesting to see how we look at that. If you are raising x to the power of n and you want to differentiate that, n sits in front and x to the power of now 1 less than n, which means n minus 1. Now, what is the derivative of x, everybody? The derivative of x is 1, so I don't have to write times 1. But if I did, remember, the derivative of x is times 1. However, if you're looking at this case, going by the same formula, n sits in front, then g of x to the power of n minus 1. But the derivative of g of x does exist. It's not 1. It's not just 1. It's g prime of x. That's really called the general power rule or the extended power rule. To make some sense out of it, I thought this would be a nice, set of examples. So if we can figure this out, we are practically in good shape. We will look at a few examples to finish that. So the derivative of sine 2x versus sine x squared versus sine squared x. One thing I want to tell you, if you're dealing with trigonometric functions and you want to differentiate, the way you read it, it could make a difference. If I'm differentiating this, I'm going to read as sine and I'm going to stop. I'm going to pause because it helps me see the answer. What is the derivative of sine? Cosine. So the answer is cosine 2x. Now, because 2x itself is a function of x, then I need g prime of x. So the g function is 2x, so times 2. Okay. Now this one, again, I'm going to read sine and I'm going to pause. Sine, the derivative is cosine x squared, because this is a function of x by the chain rule, I need g prime. So the derivative of x squared, which is 2x. And I put it in front. What about this one? If it helps, rewrite it as sine x to the second power. So you understand you're using the extended power rule. So again, let me just quickly write that. If it helps, rewrite this. So 2 sits in front, becomes 2 sine x, times the derivative of the inside, the derivative of sine, which is cosine x. And needless to say, this is equal to sine 2x, but you don't have to do that. All right. Let's look at this example showing you both methodologies, okay, dealing with what we just mentioned as the composite function and also using the Leibniz notation. If y is given as u to the power of 5, we call it a function of u. And u is 10x cubed plus 2, we call it a function of x. Using this Leibniz notation, dy dx is dy du times du dx. Notice, by the way, as far as memorization is concerned, and if you treat this as a fraction and you really couldn't, the du's cancel out. So what is dy du? So let's go back to this. dy du. Remember, y is a function of u. So what is the derivative here? 5 u to the power of 4 times du dx. Look at u, the u function, the g function is 10x cubed plus 2. So differentiate this. So times 30x squared. We are done with calculus. We are going to just rewrite things. How? We're going to change the u to 10x cubed plus 2. And then we're going to put this one times 5 in front. And we're done. Okay? Now, this is simple enough. We don't have to go by the Leibniz notation. We can actually write the composite function. But you really need to know both. So let's quickly see how it works. If I want to find the composite function, it's easy. Okay. Y is FOG. Okay. U to the power of 5, replace the U with 10x cubed plus 2. So FOG is simply the parenthesis 10x cubed plus 2 to the power of 5. Now using the extended power rule or the general power rule, okay. So I want to differentiate this. 5 sits in front. The same thing to the power of 4. And then by the chain rule, I need g prime of x times the derivative of the inside, which is 30x squared. And now you have exactly the same thing. What is the point of this question? You really need to know both methods. Sometimes it's not easy to find the composite function if it's given in that form. So you got to know the Leibniz notation as well. Okay. Here's another example, and we are going to write it in the fashion. Okay. We want to write the composite function. Okay. And identify the inner function u and the outer function f. Okay. Just for the sake of argument, we're going to do that. So I hope you realize sine, and I don't even bother to read the rest of it. I just pause, sine, and I stop. That means that's my outer function. So f of u is sine u. Sine of what? Cotangent x. So this is the u function, the g of x function. Okay. So dy dx is dy du times du dx. So dy du, what is the derivative of sine? Cosine. Du dx, what is the derivative of cotangent x? Negative cosecant squared x. Okay, and you just write it. What is u cotangent x? So negative cosine, we put the negative sign in front, okay, everybody? Negative cosine of cotangent x times cosecant squared x, you can put that in front if you want. Either way is fine. All right, and let's look at some more interesting questions. Let's start with simple ones, starting with this one. Using the extended power rule class, okay, I have it here. 50 sits in front, so 50 times the same thing to the power of 49. And then the derivative of the inside is 20x. Done with calculus. We are going to multiply the 20x by 50, put it in front. And we're done. How about this one? We rewrite it such that the power rule can be used, everybody. We rewrite it so that the power rule can be used. Now it's very simple. 1/2 sits in front, 10x plus 5 to the power of 1/2 minus 1, which is negative 1/2, by the chain rule times the derivative of the inside, which is 10. 10 and 1/2, their product is 5. Since this is negative 1/2, it goes down, becomes positive 1/2, or this expression. I'm assuming from here to here, which is algebra, nobody has any problem. Okay. Okay. We want to differentiate this. 5 is just a multiplier. Okay, let it be. So 4 sits in front, so 5 times 4, the same thing to the power of 3, times the derivative of the inside, which is 3 by the chain rule. And we're done. With calculus, we're just going to write 5 times 4 is 20 times 3 is 60. We want to differentiate the exponentials. Okay. If you look at this one, first of all, the exponential is always itself if the base is whatever. Okay, so we're going to deal with e, and then there are other things we're going to consider. For example, here, the answer is e to the power of 10x times, by the chain rule, the derivative of the exponent, which is 10. And we put the 10 in front. Okay, so the derivative of e to the power of kx is k times e to the power of kx. Okay, what about this one? Okay, and you can look at this one if you want. The derivative of any exponential is itself times the derivative of the exponent g prime of x. So what is the derivative of the exponent? 2t. So it's the same thing, e to the power of t squared times 2t. The next one, the fastest and easiest way is just to rewrite it first. It's the same as e to the power of 2t. So the answer is e to the power of 2t times the derivative of 2t, which is 2, and we put it in front. Okay, everyone? We put it in front. All right, now we can put a raised dot in between and realize that it's the product of 5x and this expression. And therefore, it uses the product rule as well as the chain rule. All right. 5x times 3x minus 2 to the power of 4. The derivative of 5x is 5 times 3x minus 2 to the power 4, plus the derivative of this piece is 4 times 3x minus 2 cubed times 3 times 5x. And again, we are done with calculus. We are going to rewrite this second piece as 4 times 3 is 12 times 5, 60x times 3x minus 2 quantity cubed. Now, this expression and the first one, what's in common? 5 is in common. 3x minus 2 is in common. What exponent do we use? The smaller of the two, which is 3. In other words, I'm going to do the factoring, and class, you are expected to be very comfortable with factoring. So 5, 3x minus 2 cubed. The first one gives you 3x minus 2. And the next one, 60, okay. You can divide by 5, gives you 12, or you can say 4 times 3 and then x. That's why I put this in green if you want to use that, or I put this in the following colors. This is a blue one, this is a blue one, this is a blue one. These are the ones left. And so now, of course, 3x plus 12x is 15x. And you're done. By the way, if this number 5 is a huge number, all you have to do is to keep it out as a multiply. How about this one? If I want to differentiate this one, I can use the quotient rule, but there is no need for that. Anytime you have just a number in the numerator, it's easier to rewrite it in this fashion. So if you happen to have a number in the numerator, it is faster to go this route. Okay, everybody? And so with that being the case, negative 4 sits in front, the same thing to the power of negative 5, times the derivative of the inside, which is 14x minus 1. So one more time. Negative 4 sits in front, the same thing to the power of minus 5, 14x minus 1. So now you have a fraction. The top is negative 4 times 14x minus 1, and the bottom is 7x squared minus x to the power of positive 5, everybody. Positive 5. Okay. All right. Quotient rule in conjunction with the chain rule. All right. The derivative of the top is 1 times the bottom minus the derivative of the bottom is 4 times 2x minus 1 cubed times 2, the derivative of the inside, times the top, which is x, over the bottom, squared. So take a look at what happens one more time. The top is 1 times the bottom, minus 4, 2x minus 1 cubed times the derivative of the inside, 2. What is this? X times the top. This is the quotient rule. And the bottom, the exponent becomes 8 instead of 4. Again, done with calculus. Let's do algebra. I hope you realize 2x minus 1 is in common, and you have exponent 4, you have exponent 3, you're going to use exponent 3. So when you take 2x minus 1 cubed out, this gives you 2x minus 1, and this one gives you minus 4 times 2x, which is minus 8x. Now, this goes away, and this changes to number 5, and this changes to 2x minus 8x, which is negative 6x minus 1. So 2x minus 1 quantity cubed completely goes away, and this is what you get. So I hope you see that there is a lot of steps that involves algebra, and you got to be comfortable with it. All right. I want to differentiate this. We have a number in the numerator, so let's just rewrite it. We don't have to use the quotient rule. I hope everybody's okay with the algebra behind this. And now what happens? Simple. 4 times negative 1/2 times the parentheses to the power of minus 1/2 minus 1, which gives you negative 3/2 by the chain rule times the derivative of the inside, which is 2x. Let's recap. 4 times the exponent. Same thing to the power of negative 1/2 minus 1. And then the derivative of the inside. We are done with calculus. We are going to rewrite this. Okay. So first and foremost, we have a negative sign. Secondly, these two cancels out this 2, and then we have minus 4x. Okay, everybody? So this one and this one gives you minus 4x. This goes down, and it's to the power of positive 3/2. Positive 3/2, and you can write it in this manner or not. All right. The power rule, the extended power rule, and here's what we have. 5 sits in front, parentheses to the power of 4, times the derivative of the inside. The inside uses the quotient rule. So let's quickly recap. 5 sits in front, the same thing to the power of 4. Differentiate this. 2 times x minus 8 minus 1 times 2x plus 3 over the bottom squared. So one more time. 5 sits in front, the same parenthesis is repeated, and 5 goes down to 4. You use the quotient rule on this. So what happens next? This becomes 2x minus 16 minus 2x minus 3, and it changes to negative 19. So what do we have? Let's just rewrite the things so everybody can see that. We are just rewriting it. So what happens now? 5 is at top times negative 19 gives you negative 95. 2x plus 3 to the power of 4 is at top. And then this one, remember this one has exponent 4, and this one has exponent 2, 4 and 2, they add up. And this is your final answer. So I hope you realize there is a lot of algebra involved. That's why calculus is a piece of cake. As long as prior knowledge of mathematics is okay, that means algebra, trigonometry, geometry, you name it, okay? All of the above. So with that being the case, how would we differentiate this? Again, I'm going to remind you the way I approach that, which is simply the way I read it. So the moment I see that, I just read cosine and I stop. Cosine, and I'm pausing. Cosine. What is the derivative of cosine? Negative sine. So negative sine of the same thing, whatever the argument, 3t to the power of 4. The chain rule says this is a function of t, take a derivative and multiply by it. So times 12t cubed. And I'm going to put that in front, and this is my final answer. Okay? Simple. All right, let's look at these exponentials. As we mentioned, it's any exponential, the answer is itself. So the answer is e to the power of 10x times 10. What about this one? The answer is itself, e to the power of 10x times, what is the derivative of 10x? Secant squared. Okay. The only thing I want to make sure everybody can see in case is that this means 2/3 x. As long as we see that, we are done. So the answer is itself, and then times 2/3. Okay, everybody? Times 2/3. So what happens if we don't have a base e? I hope you realize we are using the logarithmic properties here. Okay. As you recall, e to the power of ln x is x. Therefore, instead of a b, we are going to write e to the power of ln b. Why are we writing it in this fashion? Because when the base is e, we know what to do. When it's not, we don't know what to do. So we're going to change the b to e to the power of ln b. Now, the power rule says it's the same as e to the power of ln b times x. Remember, ln b is a number, so e times ln bx. Now this we know how to deal with. What is the derivative of that? Itself. Times, what is the derivative of the exponent? ln b, which is a number. Therefore, e to the power of ln b times x times ln b, and we are going to change this expression back to b to the power of x. What does it mean? It means if the base is no longer e, the answer is itself, but times the natural log of the base. If you happen to have a function, of course, then it is itself times natural log of the base times f prime of x by the chain rule. What do we mean by that? Let's look at this simple example. Class, y is equal to 3 to the power of x. So the answer is 3 to the power of x. That's what I'm saying. The answer is itself because it's exponential. Look at the base. Because the base is not e, then times ln b, which means the base is 3 times ln 3. And you're done. Okay. 2 to the power of 7x. It's an exponential function. The answer is itself. 2 to the power of 7x. Okay. What is the base? E? No. So times ln of the base, ln 2 times ln 2. What is the exponent? X? No. It's a function of x. So by the chain rule, I need 7. So one more time. The derivative is itself. Ln of the base. Chain rule gives us 7. Now we are going to rewrite this. And it is important to write it in front. Put them next to each other as a parenthesis because we want to make sure we don't mix things up. So this is the proper way of writing it.
Hey, Professor, is the ln, is that part of another chain rule?
No. This is logarithmic rule. Let's go back here. E to the power of ln x equals x. So b is the same as e to the power of ln b. B is the same as this one. Why are we writing it this way? Because we don't know the derivative of b to the power of x. We only know when the base is e. This is logarithmic properties. If you guys go back to the first chapter, you got to become very comfortable with the logs. Log, there were many rules, okay? Such as log 1 with any base is 0. Things of that nature, okay? There were 7, 8 rules that I have them in the first chapter. You guys got to be very comfortable with that, okay? So again, going back to this one, this is one rule. Another one was e to the power of ln x is x. Those are all properties of logs. The two of them together refer to the fact that logarithmic functions and exponential functions are inverse functions. Inverse functions. All right. We want to find h prime of 1 in this case where h of x is given. Before we find h prime of 1, and there's some information, let's find h prime of x first, and then we plug in 1. So in order to find h prime of 1, we need to find h prime of x. So what is h prime of x? We're going to rewrite this to the power of 1/2. We're going to rewrite this to the power of 1/2 to make life easy. What is h prime of x? 1/2, the same thing to the power of negative 1/2. And then by the chain rule, I need the derivative of the inside. What is the derivative of the brackets? 3f prime of x. So let's quickly recap. This is it, believe it or not. This is the only calculus part. 1/2 sits in front. You write the brackets or parentheses to the power of 1/2 minus 1 or negative 1/2 by the chain rule times the derivative of the brackets, which is 3f prime of x. We're going to rewrite this, okay, or we can just keep it like that. It doesn't matter. If you want to rewrite that for the sake of argument, class becomes something like 3 the halves, actually 3f prime of x square root of 4 plus 3f of x, just in case. Okay, but if just, you know, since you are evaluating class h prime of 1, it's probably easier to keep it like that. So replace the x with 1. Everywhere, replace the x with 1 because we want h prime of 1. In other words, I'm telling you that we are done with calculus, we are doing algebra. 1/2, 4, plus 3f of 1 to the power of negative 1/2, 3 times f prime of 1. So what is f of 1? We know it to be 7. What is f prime of 1? We know it to be 4. Let's plug in. Let's plug in. So 3 times 7, 21, and 4 is 25. And 25 to the power of negative 1/2, that means square root of 25 in the denominator. 1/2 and 3 and 4, they give us 6. So I hope you realize it becomes 6 over square root of 25. Because again, I want to make sure everyone understands why. 1/2 and 3 and 4, their product is 6. And this piece is square root of 25, which is 5. And this is the final answer. All right. Let's look at the next one. We are given the following, and we want to find the answer. So let's quickly do that, starting with the first one. The question is, what is the derivative of this function? And again, the way I read this, first I'm going to rewrite it because it may be helpful to rewrite this as cosine to the power of 10. So write it in this fashion. It is truly helpful when you do that. So 10 sits in front. 10 sits in front. You write the same thing to the power of 9. Okay, that means 10 cosine to the power of 9 of sine x cubed. Now we're going to take the derivative of the brackets. So 10 sits in front, cosine to the power of 9 of this. Now, what is the derivative of this expression, cosine? In fact, if it helps you, class, you can write this as u to the power of 10, which gives you 10 u to the power of 9 du dx, if you want to do that. Either way is fine. So now what is the derivative of this inside? Okay, inside is cosine, so the derivative becomes sine of sine x cubed minus sine x cubed. The derivative of cosine is negative sine. And by the chain rule, again, the derivative of sine x cubed is cosine x cubed, and again, x cubed gives you 3x squared. This is as involved as it gets. If you can understand this, you are done with the chain rule. So let's quickly recap. First, we write it in this fashion. Then we put the 10 in front and this thing to the power of 9. When you want to write this thing to the power of 9, you can write it like this way. So that's the first part. Now, what is du dx? Let me just write that again. I want to make sure that everybody understands what's happening here. You're letting this be u, everybody. So the derivative of this part is this. Let's see how that works. Cosine of this expression becomes negative sine of the same expression. Now sine x cubed, the derivative is cosine x cubed, and x cubed 3x squared. You're done, you just rewrite it, class. Okay, that means you have a 10, you have a negative sign, you have a 3, you get minus 30. You put the x squared in front, cosine x cubed in front, and then you can either write this in front or not, makes no difference. Now, this is an example you really need to spend a few minutes on it later on at home, okay? Part B, again, if you want, this is the argument of tangent, you can call it u. So the derivative of tan u is secant squared u du dt, okay? That means tangent, the derivative of tangent becomes secant squared of this piece. Tan gives you secant squared of this, secant of cosine t. And then now you got to multiply by the derivative of u, secant of cosine t. Now, what is the derivative? Now, remember, the outer piece is now secant. The derivative of secant is secant tangent. So secant of this, tangent of this, and then the derivative of cosine, which is negative sine. It can get involved, but again, let's actually write this. Write it as tangent u, where u is secant of cosine t. This part, when you differentiate, gives you this. The derivative of secant is secant times tangent, okay? And then the derivative of cosine is negative sine, you rewrite it. Again, this is the page you really need to work on, class, okay? It's a page you want to look at it a couple of times to be on the safe side. Here's the last question of the section. Observation shows that the length from nose to tail of a Siberian tiger is given as such. L is 0.25 W to the power of 2.6, where W is weight in kilograms. And furthermore, a young tiger's weight can be estimated in terms of its age as follows. Okay, T is in days. How long is the tiger in 100 days? This is elementary algebra, class. Just plug in 100 here, gives you the weight, and then the answer in here gives you the length. So that part is elementary. So the weight, replace the T with 100, you get 24. Now replace it in here and you have it and you're done. Also, you could do their composite function. You could do their composite function and find L of T and then plug in to find L of 24, okay, in case. All right, at what rate is the length increasing when it is 100 days old? I want you to see this part, class. This is important. The way you set up this one, this is in Leibniz notation. I'll show you both ways because they're both doable. I'd rather do the Leibniz notation. If I want to go with the Leibniz notation, at what rate the length, okay, so I'm going to write dl is increasing when it's 100 days old. That means dl dt. That's the meaning of it. So I'm going to put the dl here and then dt here. And then between L and T, what is the other variable? L is a function of W, and W is a function of T. Therefore, I need to find the W here, okay, class? So that's how you find it. Now, this is a simple calculation in both cases. DL dW would be 0.25 times 2.6 W to the power of 1.6. And then dW dt is simply 0.21. And it simplifies to this. As you can see, the LDT is a function of W instead of T. And we are not interested in finding the function. We just want to know in 100 days. And in 100 days, okay, we have the weight to be 24, so replace it with 24. And you write the units as whatever units of length per unit of time. dl dt, so pay attention to this class, dl dt, the units of length over the units of time. That's how you arrive at your units. However, since this is fairly easy to calculate the composite function, I want to show you the second method just so you see how it's done. I can calculate L of t, okay, it was mentioned here, and it's 0.25. W is replaced with this. So for part A, I replace the t with 100, and when I'm done, I get to the same answer I had here. Okay, I'm just being lazy here, I just used 1 decimal. As far as the differentiation, L prime of t, it's 0.25 times 2.6 times the same thing to the power of 1.6, and then times the derivative of the inside, which is 0.21. So take a look one more time. 2.6, okay, sits in front, so 0.25 times 2.6. Same thing to the power of 2.6 minus 1, or 1.6, and then the derivative of the inside. You can simplify it into this, and now you can replace the t again with 100. And of course, you write the units that you had over there. The point is, there are 2 ways to do that, and sometimes one is easier than the other. Okay, class? In this case, I wanted to show you that both ways are doable, but we don't have that luxury all the time, class.